Hello, everybody. So I want to talk about section 12.12 today. We're talking about polar coordinates. And we talk about polar coordinates, we're really talking about sort of changing our coordinate system, the XY plane, into sort of how we're carving it apart in a different way than we usually do. So when you're thinking about carving apart the polar coordinates, you're usually thinking about what are called Cartesian coordinates. So this is sort of named after Rene Descartes. And so the idea is that you are taking the XY plane and you've got a positive and a negative x-axis. And those real numbers are on this axis, the positive and negative y-axis. So this is another real number line sort of lined up together. And then each of the x comma y values gives me a unique point in this plane. So giving you the 0.44, there's only one place where you're going to have the 0.44. It's going to be right there, 44. So this is great. Unfortunately, it doesn't work for some functions. In fact, it's just not nice for some functions. So in particular, it doesn't take us long to find one that's kind of bad. Well, the circle is the first one we can maybe think about that kind of is a pretty awful way to describe this. So like the points on this circle pretty much don't have rational coordinates. I mean, the x and the y here are 4 and 4 for the x and the y axis. Those are perfectly normal, fine, great. But everything in between on this line here is not nice rational coordinates. And in particular, we can sort of think about how you find those things. Well, the x and the y coordinates here are kind of some multiples of you sort of got your x squared plus y squared, you square root it, and you do this sort of half circle thing on top to find y as a function of x. And then you can sort of, maybe combine that, glue that in with the negative square root to get the bottom half of this circle. And that's great. But then you're now dealing with radicals as you're trying to square root or trying to differentiate things or do whatever you're trying to do to this. It's not as nice as it could be. So our idea here is to say, oh man, that's not working out too well. Maybe, just maybe, there's a way I can divide up the plane that is more conducive to looking at these kinds of circular structural graphs. And the answer is yes, there's actually a very nice way to sort of look at these. And not only that, but we can now talk about some other functions that are stranger than just a straight up circle. So what we do is we say, all right, so to find a point in the XY plane, I needed two coordinates. I needed an X coordinate and a Y coordinate. So basically, probably I need two pieces of information in order to describe a unique line in this plane. And that's reasonable, right? Sort of, you need two directional things to sort of tell you where you are on this curve or on this plane. All right. So what are we going to do? We're going to say, all right, so I don't want to divide this up into squares anymore. So you sort of think of these things, they're little squares, but really, like, there's a point on every point on this plane. So they're not really divided up into squares, but in terms of like a discrete structure, I'm looking at little squares here. So I don't want to divide it into squares anymore. Instead, I want this to act nicely for circles. So I'm going to divide this plane into a bunch of concentric circles, meaning all having the same center. Okay. And each of these concentric circles are centered at 0, 0. And the way that I can describe which concentric circle I'm on for you is exactly what's the radius of the circle I'm looking at. Okay. What the nice thing about this is going to be is that a circle will be described by a constant. So radius 4 describes exactly the circle of radius 4. All right. So the radius is going to tell me which of these circles am I on? And radius 0 is, of course, the center of the circle. Radius 1 will be sort of the next one out, 2, 3, 4, and so on. Now, radius 1/2 is also in there. And so is radius 1 1/2. So they're all circles, just like with the other plane, there's a point at every point in this plane, and there is a unique circle on which that point lies. How do I find which point, what circle it lies on? Well, I want to know how far is it from the center of the circle, from 0, 0 to that point. Well, the distance from 0, 0 to a point is a nice, well-described thing in math. I can find the distance of this, and the distance is just the square root of the difference of the two x values squared plus the difference of the two y values squared. Well, one of the y values is 0, one of the x values is 0, so it's really just the squares, sum of the squares of the two x and y values here. So I end up with a nice radius. That radius is a unique thing. For any point in this plane, there's like one concentric circle it's going to lie on. Now, it doesn't tell me exactly what point it is. So just telling me which concentric circle it's on doesn't tell me enough information. So we need one more piece of information here. So you could say, well, maybe I could try something else, like maybe give an x value, and then that'll determine what this would be. Well, yeah, that's great and all, but it's not quite enough. In particular, for each x value, I have here, it's on a whole bunch of concentric circles, but it's actually hitting some of these concentric circles twice. So it's not really enough to sort of give you an x value and a circle it's on. So instead, we want to kind of go back to trigonometry and say, we can tell you where on a circle something lies based on an angle. And the angle is going to be the angle formed by kind of the ray from the center of the circle outward to the x-axis. And that angle measure is going to be some theta. So I'm going to divide my plane into concentric circles, and these rays sort of centered at the origin here. I sort of think there's sort of rays all throughout here. And again, there's rays everywhere. The ones that I've drawn on here are the nice ones that we not like pi over 3, pi over 6, pi over 4, and pi over 2, right? Pi over 2 is the axis, and pi and so on, right? And these concentric rays now will give me a way to describe exactly what's going on. Also, you'll notice it's not divided into little squares anymore. It's divided into like little circle segments, right? So sort of little circle segments around this thing. That's going to be very nice, because when we're thinking about things like integration, well, integrating something circular or something with a lot of curves in it, you're trying to do this with rectangles, and it's hard to do that. Instead, what about these like partial circles? These little partial circles are going to give me a good measure of the area underneath this curve, and between this curve and like the x-axis of the 0, in fact, in this case. And so we're going to have some idea of integration that's going to be pretty nice with little pieces of circles rather than little squares in there. All right. The other thing to mention here is that most of the time, then we think of like the r value is like the dependent variable. So it depends on the theta, and the theta is the independent variable. So you get to choose a theta, and it determines an r value, an r radius. So usually we think of things as like r is f of theta. F of theta, the function is going to have theta as an input. The output will be the radius. And so you can think of these things as a radius is output for each theta that you input. So you're inputting these theta values, and you're sort of changing the radius as you're going around the circle. Okay. So that's the idea, is you're sort of dividing your plane into concentric circles and rays centered at the origin to give yourself a new way of describing which point in the plane I'm talking about. Okay. So from trigonometry, if I have a point on this thing, we can find the x and the y value. So to find the x and the y value, I have an r and I have a theta. So the x and the y value are going to be determined as the other two sides of this triangle, this right triangle here. And it turns out, so we know that like cosine of theta is going to be, x over r. So that means that x is just r cosine theta, because cosine is just adjacent, which is the x value, over hypotenuse, which is the radius, the r. So I just get x over r. So I just get x is r cosine theta. Similarly, sine of theta is opposite over adjacent, which is just y, or opposite over hypotenuse, excuse me, is y over r. So y is just r sine of theta. Okay. So this is nice. So what we get out of this, if I have an r and a theta, I can tell you the x and the y value at that point. So I can convert between polar coordinates back to these Cartesian coordinates, the x and the y axis, the x and the y values. All right, so this is really good. If I have a polar coordinate, I can find the Cartesian coordinate. Unfortunately, the other direction is not as straightforward. I can do it. So I can convert from polar coordinates from Cartesian coordinates. So I can go to polar coordinates from the Cartesian coordinates. I have a good radius. The radius is just the square root of x squared plus y squared, all under square root. But the theta is not so nice. So the theta is determined by the tangent of theta is y over x. So that's opposite over adjacent. Unfortunately, that theta depends on the quadrant. And if I were to do this and take the inverse tangent of both sides here, so if I do the inverse tangent of both sides here, well, the inverse tangent only lands between negative pi over 2 and pi over 2, not including negative pi over 2 and pi over 2. And so I don't actually get anything in quadrant 3 or 4. Or sorry, in quadrant 2 or 3, right? So in quadrants negative pi over 2 to pi over 2, this is sort of in quadrant 1 and quadrant 4. So I'll get those angles all right. But then anything in quadrant 2 and in quadrant 3, I'm not going to get out of this inverse tangent function. So I have to do a little bit more beyond just saying, oh, do the inverse tangent and you're done. I have to think about what choice of theta do I get. Plus, that choice of theta is not even unique. I can go around the circle again, an entire 2 pi rotation there, and that will give me another angle that has that same property. I can go around it backwards as well. The other thing I'm able to do here is I could also take r to be the negative square root. So take r as a negative number, and then land in the quadrant that's like opposite the one I'm aiming for. So if I want something in quadrant 1 and I have a negative radius, I go to quadrant 3, because now in quadrant 3 I'm going to be down here, but then the negative radius is going to flip me across and put me in the positive in quadrant 1. Okay, so we have a couple of sort of hiccups here at the end. The choosing theta depends on the quadrant, and it's not unique. And in particular, that r could be negative, and so that's okay. We just choose that the theta that's going to be kind of like a dipole of that other angle. It's in the other opposite quadrant of what I actually want it to be in to find the point that I want. So let's do an example here. So here are some coordinates that are polar coordinates. I can convert them to Cartesian coordinates. This is not a very difficult thing. So here, the first one is radius is 1, theta is 5 pi over 4. So x, the x value we have is just r cosine theta. The y value is just r sine theta. And if theta is 5 pi over 4, 5 pi over 4 is in quadrant 3. So 5 pi over 4 is just past pi, right? So it's 1 pi over 4 beyond pi. The reference angle is pi over 4. So the tangent's the only thing that's positive. The sine and the cosine are both negative there. Radius is 1. And I get cosine of 5 pi over 4 is negative cosine pi over 4, which is just a negative root 2 over 2. And then sine has a 1, and again, a negative root 2 over 2. So that is, again, the opposite sign of what I would want, because it's in opposite sign of the original, because it's in quadrant 3. All right. So what I would answer here in my question is I would say, oh, the coordinates for 1, 5 pi over 4 are 1, or just negative square root 2 over 2, comma, negative square root 2 over 2. So the x and the y coordinates are the same. They're negative root 2 over 2. And that's it. You can do the next one as well. So the radius there is negative 5. So x is negative 5 cosine of 5 pi over 3. And the y is negative 5 sine of 5 pi over 3. Okay, 5 pi over 3 is in quadrant 4. So we go here, 5 pi over 3 is all the way down there in quadrant 4. And so sine will be positive, cosine will be negative. So what we will end up with here is negative 5 and then negative, or sorry, cosine is positive. So it's cosine of 5 pi over 3, which is the same as cosine of pi over 3. The reference angle is pi over 3. And then this is going to be negative 5 times negative the sine of pi over 3. So again, the reference angle is pi over 3, but this is going to be negative because it's in quadrant 4. Okay. So what we end up with here, we get negative 3 over 2 and 5 root 3 over 2. Right. And that value should be negative 5 over 2. Okay. And then the last one, 2 is the radius, 5 pi over 6. So you get negative root 3 and 1. So 5 pi over 6 is in quadrant 2. So that means that the cosine is negative, the sine is positive, and so it's going to work out. Okay. So going backwards, we have this problem. We don't have a unique point here. So there's not a unique way to describe 2, 2. So I can do this. I basically say, okay, so the radius I can find sum of x squared plus y squared. And so that's going to be 2 square roots of 2. So it's 4 plus 4, which is 8. Square root of 8 is 2 root 2. Okay. And then theta, well, the tangent of theta will be pi over 4. Or sorry, will be 1, 2 over 2. You just get 2 over 2 there for the tangent, which is just 1. And so the inverse tangent of that is pi over 4. So one way to describe this point is radius 2 root 2, angle pi over 4. Another way to describe this would be radius 2 root 2, angle 9 pi over 4. So add 2 pi to that thing. Another way to describe this is negative 2 square roots of 2. And then I take, instead of pi over 4, I go into quadrant 3. So pi over 4 is in quadrant 1. So I want to land here. And if I have a negative radius, I need to land here. And then it will flip across when I do the negative radius. And so what I need here is the angle down here in quadrant 3. And the angle in quadrant 3 is just 5 pi over 4. And then I could sort of do any 2 pi additive of that, or subtract 2 pi from that and just get what I need. All right. So there's an infinite number of ways to do this. You sort of have a lot of different ways to do this to get that out of there. And this is wrong. It should be 2 root 2. And negative 2 root 2. I don't know why. All right. Cool. So how do we describe functions in polar coordinates? So functions in polar coordinates are basically, like I said, r equals some function of theta. So r equals something with theta in it. Circles are the easiest things to describe. So a circle centered at the origin of radius a is just r equals a. So this is great. To find a circle that's not centered at the center at the 0, 0, it's a little harder. Not terribly bad though. It's just 2a cosine theta, 2b plus 2b cosine theta. The advantage to this is these are both just functions. There's no square roots. There's no squares floating around in here. There are squares when I like find the radius, but I don't care about that. That's like just a number, right? So whatever that number is fine. This has no squares and it has no square roots in it. So the derivative of this thing, if I differentiate with respect to theta, is going to be fine. It's going to be easy to do, right? And a and b are just constants, so it sort of just all goes through really nicely. So that's sort of an advertisement of why we care. So to do all of this stuff is great, but why we do this is because we can treat things that are not functions, y is a function of x or something like that, as functions. R is a function of theta. Okay. And then we can graph these things. So the suggestion in the book is to graph r equals f of theta as though r is y and theta is x, and then we kind of look at these to plot the points on a polar coordinate plane. That's fine. You can do that. I personally, if I'm doing this by hand, I will make it like an r and a theta table, and I'll just plot points that way. For me, that's a little bit easier because that's all you're really doing when you're sort of graphing this thing on the xy plane and then converting it into the polar coordinates. So I might just do that, or I just do it on a computer or a calculator. And so you can actually do this on something like Wolfram Alpha. So you just go in here and you say, I'm going to polar plot of just r equals 4. And so if I do r equals 4, what I'm going to get out of this thing is a circle centered at the origin. Radius is just 4. Okay, and then it takes theta from 0 to 2 pi. It in Wolfram Alpha, it will do it nicely. It'll tell you sort of, then it'll try to plot it as nicely as it can. If you're doing it by with your calculator, you might have to go in and change the theta values. So you might say, oh, maybe theta doesn't go far enough or something like that, and kind of go from there. You can play around with this a little bit. And so you can sort of see there's sort of 4 sine theta. That changes things a bit. So notice all that has done is it just moved up the circle a bit. And we can do maybe put a 3 inside there, 4 sine of 3 theta. Now we've got a little bit different. You can sort of see some strange stuff coming in here. This is kind of cool, right? So we have this sort of nice flowery shape, essentially, out of all of this. We can try anything else. So just get in there and try some stuff. I think that's kind of a good way to do this. Try something like sine cubed 5 theta or something like that, and just see what comes in there. Yep. So you can sort of see there's a nice little triangle there, or a nice little again, it's a flower in there. If I do say sine to the 4th, so an even power of sine with say 4 theta inside of it. There we go. So sort of a little bit more structure coming into this. That's kind of cool. What if I maybe subtract off cosine of theta? Let's go with cosine of 3 theta. See what happens. Again, you can try this and sort of see what you can mess up and sort of see what's going on. So what's happening here is that the cosine is not going to be the same sort of 1 and 0 values as the sine, and so the sine is going to be kind of moving out farther at certain points, and the cosine is going to be moving out farther at other points. So you're going to get this sort of smaller pieces of this graph with bigger pieces of the graph as well inside there. So it's kind of cool. So you just go in there and play around with these things and see what you can come up with. They're definitely a lot of fun to play around with, so you can see what's going on. Cool. And then if I can sort of maybe advertise one more time, imagine if you were given some piecing together of x and y functions in here to create this graph. I'm pretty sure you're going to have a whole bunch of square roots in there, at least square roots, if not 4th roots, 3rd roots, something like that. And then you're going to have to maybe find, I want to know what is the tangent line to this curve at that point right there. Well, that's going to be pretty awful. So I'm going to have to basically choose the right function, figure out which is the right function that we have to use to define this thing in terms of y is a function of x, as some function of x, right? And then I'm going to have to do derivative, and then I'm going to have to solve for the point where that is, and then I'm going to have to use that to find the equation of the line. We're going to skip all of that, and we're going to be able to do some sort of derivative with this thing in it. And then we're going to say, hey, that's going to be the slope dy dx. And then I'm just going to be able to find the point. And then I can look at this thing and say, well, the y equals mx plus b, that will be the line tangent to this curve through that point. Okay, and there we're talking x and y as Cartesian coordinates, not as polar coordinates. And so we really are kind of changing coordinate systems back to the polar coordinates, to the Cartesian coordinates here. I can also describe this line as a polar coordinate line, but it's not as straightforward as just y equals mx plus b. So we just kind of are going to do that. That's actually on the homework for this week. What is a line? What does a line look like as a polar coordinate system? It's kind of cool. All right. So with that, I'm going to leave you with it and go see what you can do with the homework. It should be pretty fun, I think, and play around with these polar coordinate planes. See what you can come up with. There's a lot of fun stuff to come up with. All right. Thanks.